Welcome to Beyond the Brackets. Today we are diving into Bernoulli's equation, a special type that can be transformed into linear equation. An equation of the form dy by dx plus py is equal to q into y power n is called Bernoulli's equation, where p and q are functions of x or constants and n is a real constant. Let's start with the first problem. Before solving, let's identify the type of equation. Comparing it with Bernoulli's equation, we know it's a first order differential equation that includes dy by dx, a y term and a y power n term. To bring this equation into Bernoulli's form, we should make sure there's no coefficient with dy by dx. So we'll divide the whole equation by x. Now it becomes dy by dx plus y by x is equal to x square into y power 6. It is of the form dy by dx plus py is equal to q into y power n. Solving a Bernoulli's equation always follows the same basic steps. First, we divide the whole equation by y power n. Here n is 6. So dividing the entire equation with y power 6, we get 1 by y power 6 into dy by dx plus 1 by y power 5 into x is equal to x square. After simplifying, we'll notice a pattern. There's a dy by dx term with a y coefficient and x term with a y coefficient, and the RHS is purely in terms of x. Now in the second step, we identify the y term that comes with x and that is taken as u. So we get 1 by y power 5 is equal to u. Although this relation involves u and y, differentiation is always performed with respect to x. Differentiation of y power minus 5 will be minus 5 into y power minus 5 minus 1 dy by dx is equal to differentiation of u will be du by dx. When we simplify the differentiated term, our aim is to get the value of this term. So 1 by y power 6 dy by dx is equal to minus 1 by 5 du by dx. Substituting these values in equation 2, we get minus 1 by 5 du by dx plus u by x is equal to x square. The equation is now transformed into linear differential equation. To eliminate the coefficient of du by dx, we multiply throughout by minus 5, resulting in du by dx minus 5u by x is equal to minus 5x square, which is a linear equation of the form du by dx plus pu is equal to q, where the coefficient of u is taken as p, that is minus 5 by x, and the RHS is taken as q, that is minus 5x square. For the linear differential equation, integrating factor is given by e power integration of p dx. So e power minus 5 will be constant, integration of 1 by x dx. So e power integration of 1 by x will be log x. Again, a log p can be written as log p power a. On simplification, the integrating factor is 1 by x power 5. For this linear differential equation, solution is given by u into integrating factor is equal to integration of integrating factor into q with respect to x plus c. Substituting the values of u, integrating factor and q, x square and x power 5 cancel out in the numerator and the denominator. So we get integration of x power minus 3 with respect to x plus c, which will be x power minus 2 by minus 2. That completes the solution for the first question. Now moving on to the second problem. Name the equation as equation 1. We observe that it is of the form dy by dx plus py is equal to q into y power n, that is Bernoulli's equation. So for the first step, we divide the entire equation with y power n. In our case, this is y square. So dividing throughout by y square, we get 1 by y square into dy by dx plus 1 by y into tan x is equal to secant x. For the second step, we take the coefficient of x term, that is 1 by y is equal to u. And this will always be differentiated with respect to x. Differentiation of 1 by y will be minus 1 by y square into dy by dx is equal to differentiation of u will be du by dx. Our aim is to find this value. So 1 by y square dy by dx is equal to minus du by dx. Substituting this in equation 2, we get minus du by dx plus u tan x is equal to secant x. Now the equation is a linear differential equation. We don't want the coefficient of du by dx to be negative, so we multiply the whole equation by minus 1. This linear equation is of the form du by dx plus pu is equal to q, where p is the coefficient of u, that is minus tan x, and q is the RHS, that is minus secant x. Integrating factor is given by e power integration of p dx, e power integration of minus tan x dx. Tan x can be written as sin x by cos x. We know that differentiation of cos x is minus sin x, so this is of the form f dash of x by f of x. So integration of this will be log of f of x. So e power log of cos x will be equal to cos x. For this equation, solution is given by u integrating factor is equal to integration of integrating factor into q with respect to x plus c. Substitute the values of integrating factors u and q. Cos x cancels out in the numerator and in the denominator. So we are left with integration of dx, that is x plus c. Let's quickly look into the last question. After naming the equation as equation 1, we observe that it is a Bernoulli's equation of the form dy by dx plus py is equal to q into y power n. So for the first step, we divide the entire equation by y power n, and in this case it is y cube. So dividing throughout by y cube, we get 1 by y cube into dy by dx plus cos x by y square is equal to sin 2x. For the second step, again we take the coefficient of x term, that is 1 by y square as u, and this will always be differentiated with respect to x. So differentiation of y power minus 2 will be minus 2 into y power minus 3 into dy by dx is equal to differentiation of u will be du by dx. Again our aim is to find this value. So 1 by y cube dy by dx will be equal to minus 1 by 2 du by dx. Substituting this value in equation 2, we get minus 1 by 2 into du by dx plus u cos x is equal to sin 2x, which will now be reduced into the linear equation. To make du by dx free from coefficient, we multiply throughout by minus 2. So we get du by dx minus 2u cos x is equal to minus 2 sin 2x. It is linear equation of the form du by dx plus pu is equal to q, where p is the coefficient of u, that is minus 2 cos x, and q is the RHS, that is minus 2 sin 2x. Integrating factor is given by e power integration of p dx, which will be e power minus 2 integration of cos x dx. Integration of cos will be sin, so it will be e power minus 2 sin x. Solution for this equation is given by u into integrating factor is equal to integration of integrating factor into q with respect to x plus c. Substitute the values of integrating factors u and q. To further integrate this, we can replace sin 2x by 2 sin x cos x. While we are integrating with respect to x, notice the term e power minus 2 sin x. The power of the exponential, that is 2 sin x, will be taken as t. Differentiating with respect to x, differentiation of sin x will be cos x dx is equal to dt. Substitute these values in the integral, it becomes minus 2 integration of e power minus t. Sin x will be t by 2. 2 cos x dx will be dt. 2 in the numerator and in the denominator cancel out. We are integrating two terms with respect to t. According to Eilert rule, t will be the first function and e power minus t will be the second function. Integrate this, write the first function as it is and integrate the second function. So t into e power minus t by minus 1. We now differentiate the first function and integrate the second function by taking alternate signs. So minus differentiation of t will be 1 and integration of the second term will be e power minus t divided by minus 1 into minus 1 will become plus 1. E power minus t is common for both the terms, so we get e power minus t into t plus 1. Replace t with its value, that is 2 sin x, concludes the solution of this question. Additional problems along with their corresponding answers have been provided for further practice.